I think let me finish like this is lecture 7, lecture 8, lecture 8, lecture. I think this is lecture 7. Lecture 7. Okay. There are total like 12.
We still have 30 slides.
30 slides. 30 slides.
Yes.
I talk too much. Okay, don't worry about it. Okay. Maybe I'll give the exam when I in America. I have to escort the president go to America. Okay, we find a week when I was not in Taiwan. I'll give the exam. Okay, that is about 3 weeks from now. Yeah, 3 weeks from now. All right, don't worry about it. Maybe it will be take-home test. Take-home test will save a lot of pain. Okay, let me think about it. And night we're close now because I feel hungry. Okay, my blood sugar is very low now. Okay. All right, the cell delay model. Okay, we already know all the information we need, but still, we like to make things simple. The simple way is likely to be the effective way. So how do we make it simple? So it's quite easy. We like linear function. We hate hyperbolic function. We hate polynomial. We like it simple. Okay, simple is a straight line. That's a simple one. Everybody likes linear transform. So how do we do that? Okay, according to the equation that we already developed, we already show you. So basically, the time constant is equal to R times C. Okay, if you want to make it more precise, times 0.69 or 0.7, that'll be fine. Basically, we know that time constant. So, well, I'm sorry, I deliberately saved 0.7 from the equation, but you know what I mean. Okay, so no matter it's a high to low or low to high propagation delay, it is equal to the R times the CL. And we know that CL covers 3 terms: self-loading, while loading, and fan-outs. So we plug in all the numbers into it. This is self-loading, this is while load, and fan-out load. So basically, we can simplify it. Okay, this is a constant because this is fixed number. This is fixed number as well. It's R equivalent, and this is a C load generated by myself. The only variable in this assumption is that we have a B term over here. B equal to this one, and this is equal to the CL. And CL equal to the CY plus C fan out. So A, this term, stands for parasitic delay because this term is a delay created by itself. Let me repeat again. Every gate, even though that is a driver, it has parasitic capacitance and resistance, of course. It will generate a delay by itself. It's called a parasitic delay. Okay, no way you can get around that. And for the second term, that is composed of a while loading and the fan-out loading. We use a term to cover it. It's called a C load. So C load means an effort load, effort delay. That means, okay, you need to work hard to shorten the delay. Okay, the effort. So it's an effort delay. So parasitic delay is a DC term. Okay, it's a fixed number. However, for those effort delay created by the while load and the fan-out load, it's a linear equation. This is called the effort delay. So remember that all the delays can be simplified, okay, systematically into these two terms: parasitic delay and the effort delay. That's all. And we have a linear equation for that. And I'm going to show you another way to do the effort analysis for this part. Okay, so this is something you got to remember. It's called the cell model. And besides the cell delay model, and another guy which called Elmo, I'm sorry, not yet. Okay, so F04. FO4 means that fan out equal to 4. The 4 is 4 times of myself. For example, in this case, this is a single inverter, a unit one. And if it is used to drive n times of the same inverters, it's called the fan out N. But usually, we like to use it 4 times, and we have a theory behind that. Okay, basically we're going to deliver a signal from inside to external world. Use this way: 1 time, 4 times, 16 times. Okay, remember the size I asked you to do in the first or maybe the second homework assignment. Okay, increase by 3 times, something like that. Similarly, so this is the input, and this is the unit buffer. They will enlarge the size by 4 times. Okay, not enlarge the size, inside the number by 4 times, and 16 times all the way up. Okay, the fan out of a gate equal to the number of the same gates it can drive. That's the definition. Fan out of 4 means that a single inverter is going to drive 4 inverters, identical inverters. Fan out of 4 for NAND gate means the same thing. A single NAND gate is going to be used to drive 4 identical 4 NAND gates. Okay. Okay, Elmore model. This is a smart guy. So Elmore delay model. Okay, it all starts from the analysis of a single piece of metal wire. This is a very interesting model, and you got to remember that. And there is a very interesting, or I should say philosophical observation after this equation. So this is a single piece of metal wire, or any wire, whatever. Okay, every segment can be modeled as R and C. There is no inductor, because we don't care about a high frequency signal. That's why. So in the first segment, we use R1 and C1 to denote the first segment, then R2, C2 for the second segment, and all the way to the end. So my question is, okay, what is the delay? Okay, when we have when we have a pulse, okay, appear at the Vin, and what is the delay for the output to see that pulse? Okay, what is that? So already you already have an answer over here. It's very easy to understand this. Why it looks complicated, but in fact it's not. Okay, I'll tell you how to do the analysis. It's quite easy. You picture this, okay? You picture that all the capacitors as a bucket barrel, okay? And all the R's, all the resistance are pipes. So for the guy sitting in the end of this row waiting for the water to drink, how long he has to wait? How long he has to wait? Okay, he has to wait until all the buckets before Cn, okay, to be fulfilled, then he can drink the water. You see my point? If you pump the water from the left to right, so how long that guy sitting in the end to drink the water? He has to wait for the first bucket is full. Then the overflow of the water will go to the second bucket, then the third bucket, then all the way to the end. Is that right? Is that right? Otherwise, he cannot drink, because until all the buckets before the poor guy, they are full. Okay. Otherwise, he cannot drink the water. So this is how it works. So this is how it works. Okay. So it can if they are all the R's and I's are the same. So what's going to happen? Okay. For the first bucket to be full, this is a time constant, R and C. For the second one has to wait for the first one to be fulfilled, then he can drink, he can get the water. Right? And all the way up to the last one. So this is a delay for each segment if they are assumed equivalent. So this is overall solution. See? And N times RC, that's the last one, the second one, all the way down. And add them up together, become a very interesting but a simple equation over here. It's half of N times N plus 1. And this is equivalent to N squared RC. Remember the transmission line theory that I told you about maybe 1 lecture, 2 lectures ago? That the delay on a transmission line is not proportional to the length. It's proportional to the square of the length, and this is why. Okay, this is why. So the longer the while, okay, of course, the longer the delay, but it's not linear. It's a square rule. Okay, it's a square rule. This is Elmore delay, N squared times RC. Okay. All right, this is a single piece of straight wire, straight lines. So what if we have a tree? What if we have a tree? So we can analyze every branch of that tree. Okay, when the delay is done, okay, all the leaves of that tree drink the water, then it's done. So we got to do it. Okay, everybody, the delay over here. This is delay over here. This is delay. Delay D3, 1, 2, D3 is this one. 1, 2, 3, see that? R1, R2, R1, R2, and C2 over here. This is 1 over here, C4 over here. And then this is 1, this is a 2. Okay, this is a summation. So this is to the analysis. It's almost the same. Okay. So the RIK equal to the RJ. RJ belongs to the path from I to S and K to S. Okay, you have to add them together. Okay, this is how the rule is. It's called the Elmore delay model. So how do we use it? This is how we use it. Remember we have a complicated gate? Okay, so this is a 1, 2, 3, 4. This is a 4 inputs NAND gate. Okay? Which one is a critical path to create a longest delay? Definitely, this will not happen in the parallel cases because for the power supply to the load, it's very short, only 1 transistor delay. The longest delay will show up where that is, the discharge over this line. Okay, that will be the longest delay. And as I said, okay, all the time in this class, we always consider the worst case. So the worst case that you have to consider is this one. V in goes through the CY, CX, CW, and C out. Okay, Y, W, C, Y over here. X, W, and C out. So this is the longest delay. And follow the same derivation, you get this one. So the RZ, we have to go through 1, 2, 3, 4 buckets. And RY will go to these 3 buckets. RX goes through these 2 buckets, and this is the last one. So you add them together, that is the delay. Okay, and they are all composed of RC terms, with a summation, that's all. So the high to low delay, this is the worst case delay in these circuits as such a big number, okay? So Elmore delay model is very useful in a lot of analysis. Okay, after the delay, we have discussed about another thing, power. Remember I say there are 2 directions of your research. The first one is speed, the second one is what? Power. And power is the future. Okay. That is why our government, your beloved government, always emphasizes the green power, blah, 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 blah. But, well, personally, I don't appreciate what the government said about the green energy. What they say is not true. I'm sorry, it's not true. I'm a scholar, I have to tell you the truth. Well, do you know how much you pay for every kilowatt for your electricity bill in Taiwan? Do you know that? And you don't care. Okay, electricity bill, you don't care because your parents pay for that, right? Every kilowatt. Okay, I'll tell you the number. In Chinese, we call it degree, or use a degree, that's fine. Okay, in fact, the correct term is kilowatt. Every kilowatt, we pay 2.5 NT dollars. That is really low. I think this is the lowest electricity bill in entire Asia. Do you know, one of the TAs is from Philippines. Do you know how much they pay for every kilowatt, every degree of electricity in their country? 7.0. It's about 2 to 3 times. Philippines. All right? In Japan, it's about the same number. In South Korea, the same. I don't know about North Korea because North Korea is a mysterious territory. We don't know that. Okay, they have a very interesting stuff. In China, it's still higher than Taiwan's price. Southeast Asia, or higher than Taiwan's electric price. But how come we have such a low price? Because our government uses the taxpayers' money to pay for it. And if the government try to raise the electricity bill, okay, definitely they will lose the next campaign. Okay, so none of the parties want to do that when they are in charge of the authority. They don't do that. But this kind of thing shall never happen because it's not right. Basically, this kind of system means that we take away the money from the poor guy's pocket to compensate the big industry, those big guys in industry. That's very, very bad, and it's not right. It's not well justified. And then the government told us that they are going to push the green energy in the future. So they call that we are not going to have any nuclear energy the 2025 or 2030. I don't remember what they say. But the thing is, if you take away the nuclear energy or rely on the wind power or the solar power, do you know what is the cost for every kilowatt of the solar power and wind power? Do you know that? The cost is $4.5 per kilowatt. That is almost 2 times of the cost that we pay for now. And we are asking the government cannot raise the electricity bill price, and who is going to pay for that? The deficit, all the taxpayers. And sooner or later, we are going to be bankrupt. At least the Thai power company, they cannot hold on it. All right, this is really bad. I don't know who is going to solve the problem. Everyone, every people on this island likes to have a very low, cheap electricity bill, but that's impossible because we don't have natural gas, we don't have oil, we don't even have a geology heat. Okay, the geology heat that we have is a volcano. Okay, you want to use that? It's impossible. Okay, I don't have a solution. Don't ask me. I'm not the one paid the with $1,000 of pay per year. Okay, I'm just a poor professor, but I know what the problem is. The problem is that the cost structure of the energy right now in Taiwan is not justified. Okay, it's not justified. It's going to be bad, and no one seems to care. That's fine. Okay, it's none of my business no more because I'm going to retire in 5 years. Anyway, go back to the participation. So for your circuits, okay, you can make it very low power. That's very attractive, very sexy. So let me tell you what the difference between the power and the energy. Because from time to time, students always get confused about these 2 terms. Okay, power is drawn from a voltage source and attached to the VDD. That's called the power. So the power is basically an instantaneous power. Power is related with time. power is related to time. I'll give you some example. Okay, what is your weight? 80 kilo? Sorry, 80 kilo? No? Okay, 80 kilo, never mind. This young man weighed 80 kilo. And the old lady over there, I'm sorry, I don't mean you. Okay, old lady she's also 80 kilo. And for you to climb to 8th floor, you only need like 1 minute from 1st floor to 8th floor, right? For the old lady, she has to take 1 day to climb from the 1st floor to the 8th floor. Okay, which one consumes more power? The fat dude or the old lady? The fat dude, of course. Because the final energy is the same. They both are weighed 80 kilos. They are finally in the 8th floor. The height is the same. But the fat dude spend 1 minute. The old lady take 1 day. So the energy, okay, over time equal to the power. So the power means the measure related to the time, but energy does nothing to do with the time. So this is the difference. So the power equal to I times V, okay, with respect to the time, and the energy is the integration of over time. So this is a definition, and this is the difference of these two terms. So you got to understand what we are talking about. Is it power or is it energy? Okay? And the average power is the energy over a time span. That is how we define it. Energy over E over T, okay, is the integration of power over time, then divided by time, by T, big T. Okay? Is that clear? Okay, so this is the definition of energy and power. All right, so, and this is the power, okay, in the circuits. So the top one is the power provided by the power supply. Assume that the VDD is a constant. So it depends on how much current you draw from the power at a certain time. And of course, it can be replaced with a V square over R or I square times R. It depends on which term you like to use. And for the energy, it's an integration from time 0 to infinite for these two, I times V, right? And I equal to C times dV over dt. C is a fixed number because it's a capacitance, okay, existing in your circuits, dV over dt. So right now, if we integrate from 0 to Vc, then we got this number. Okay, remember that. Every energy spent on charging of a capacitor equal to 1/2 of the C times the final voltage of the capacitor. You got to remember this one. Okay, so that this one is going to help us a lot. Okay, so the energy for capacitor to be charged to voltage C, this is the energy you need. Okay, there is no time for that. No matter how long you take, 1 year is the same. 1 second is the same. Okay, this is the final energy. All right, remember this term, half of the CV square. Okay, now let's use this equation to the simple circuit, which is a driver to drive a load. Okay, so the energy stored in the capacitor, according to that equation, is equal to 1/2 of the C load times the V square. Is that right? Because the final voltage of the CL over at the VR is equal to the VDD. But the energy we take from the power supply is the integration of this one, equal to what? CL times V square. Okay? So now this is interesting. The final energy stored in this capacitor is 1/2. But we need to take okay, the energy from the power supply to do that kind of charging job is CL V squared. So this is the final energy that we kept in the capacitor is only half of the energy we take away from the power supply. Then where is the other half? It's gone. It becomes heat. So the more often you take it from the power supply, that means that the charging and discharging is fast. That means the more heat you generated. So the high-speed circuits, okay, will give you a lot of a heat problem. So that is why your CPU, which is claimed to be gigahertz operation, it'll become very hot. You need a fan to cool it down. That is why. So charge, discharge. Now, when you charge it, okay, you lose half of the power supply. You lose half of energy taken from the power supply. And after you discharge, those energy you store in the capacitor is also gone. So every cycle, every clock cycle, you take away the full energy, like this one, from the power supply. That is the conclusion. Okay, put it down. Okay? So how do you make a low power circuit? It's very easy. Okay, reduce the frequency. You take the energy from the power supply. Reduce the voltage. That is why when I was a student, the technology back then needed a 5-volt system. Right now, the system uses 1.8. So if we can cut the power supply into half, that means we save 3/4 of the power. That's amazing. And the third way to reduce the power is what? To make the C small as possible. When C is small, that means the area is small. So the smaller the circuits, the more power is saved. So there are 3 ways to save the power. Reduce the frequency, reduce the size, and reduce the voltage. That's the 3 ways to do that. In the meantime, you still have to keep the performance. That is hard. So half the energy from the VDD is dissipated in the PMOS transistor as heat. The other half stored in the capacitor. When the output drops, the energy in the capacitor is dumped to the GND, and the heat is generated in the MOS transistor. Okay, so this is the digital circuits energy behavior. And remember, I asked you to do the simulation. I think your TS already tell you how to do the current monitoring. This is the VDD, CL, and frequencies 1 gigahertz. So you're going to see what? This is the input, okay, and this is the output corresponding. And the shape is not that clear, it's not that good. And this is what? The currents. This is the current over there, see that? Okay, saturation, linear region, and the short circuit currents. Okay, and this is the power. There's a power over here. This is a current, another current. Charging, discharging. And if you like to have the direction, that's this way. That's this way. So the current, the biggest current you can find in this kind of a switching activity, the peak current will occur at the rising edge and the falling edge of the signal. Okay, the switching waveforms. So that is why I asked you to do the exercise to find out the current. All right, so what are reasons to have power dissipation besides the switching? In fact, there are many reasons that we dissipate the power. Basically, we divide the power dissipation into 2 categories. The first one is called the static. The second is dynamic. The first one is nothing to do with your circuit operation. As long as you turn on the power, okay, these are the power you have to waste. Okay, first thing is the leakage. Leakage is everywhere. Just like there are always water leakage in your house, okay, in every building. I'll give you the number. You might be interested. All the leakage, water leakage happening in Taiwan, okay, the overall amount of that water is about 6 times of a water dam in Taipei. The Feichuizui Ku, 6 times the water leakage. It's amazing. Okay, and gate leakage. Okay, gate leakage. Number 3 is kind of tricky. It's called the subthreshold. That is the leakage when the MOS transistor is slightly turned on, but not fully turned on. Okay, it is in the region of the linear. A linear region is called a subthreshold of the current. So the top category is nothing we can do about it, but the thank God, compared to the second one, it is kind of small. Or unless you use a very advanced device, advanced CMOS process like a FinFET or this kind of thing. So you don't have to pay attention to that. But for the second one is called a dynamic. Dynamic is the power that we need to charging and discharging the load. That is what I just showed you, to charge the low cap or discharge the low cap. Okay, the switching transient, we call that a short circuit currents. Okay, so these are dynamic. They are the main reasons that your circuits, your chip become really hot when you run out of speed. So basically, the overall power dissipation is composed of these 2 terms, static and dynamic. Okay, dynamic is about 2 parts, charging, discharging, and the short circuit currents. Okay, these 2 parts. And compared to, if you want to make a comparison of these 2, this one is much bigger. Okay, much bigger. Okay, this figure is directly copied from the textbook. That is where the leakage is. But basically, all you have to do is that you know where they are, and you don't have to do the estimation about this part. Because right now you are just at the beginning stage, so I don't think this will give you any problem. Okay, just know what's going to happen. The gate leakage and the subthreshold leakage over there, and the junction leakage is over there. That's all you need to know. But when the number is really big, that is when you are going to design someday in the future. Maybe some of you will become the superhero in IC design. Oh, I tell you what, the MTK, president, Mr. Chai, Dr. Chai, recently he has announcement, or he has important suggestion to the government that if Taiwan's government still don't pay attention to the IC design business, we might be in trouble. IC design of Taiwan might be in trouble because, well, the Red China is coming up. Okay, and that's serious. Okay, I'll give you some numbers. Remember the stacks I gave you in the first class? Okay, who is not the leader of the IC design business? American. They have a 60%. Taiwan is the number 2. It's a 10%. Okay, 60, 20. And the other 20 goes to South Korea, Red China, and Singapore, maybe some European company. But the China, well, this is kind of ugly. China, the market share of China right now they started from very low market share, like 0.1% before. Recently, they hit like a 4%, maybe 5% of the market share. You do know who are the one to help them? Taiwanese. Because a lot of Taiwanese companies send experienced engineers to China to recruit Chinese students. Okay, because they don't have enough number of IC designers in Taiwan. Of course, they want to go to see whether they can recruit talents in China. I'll tell you what, okay, before the COVID-19, every year, my lab had one student from China to my lab to do the training and exercise. Okay, of course, we told him and told her, lady students as well, how to do the design. And these students, when they went back to China, they were, according to what I said, they were hired by MTK in China. So that's why I know MediaTek and the other company like Focaltech, they have branch office and IC design division in China as well. Do you know how much they pay? Okay, they double the salary of Taiwan. Of course, they can attract a lot of young talents to work for them. All right? So I don't blame those companies. They need help. They need young men. They need the fresh legs and the fresh levers, okay, to help them. But our government, no matter who will be in the power, they should pay attention to this business. We cannot put all the eggs in a single basket like a TSMC. Right now, TSMC, they have the world-leading technology in silicon process. That does not guarantee, okay, no one is going to catch up, okay, in the next decade or next century. So you got, invest on other areas of semiconductors, IC design, and the second one, I suppose, that government should pay attention to is the compound semiconductor, the silicon carbide and gallium nitride. And I have spoken to many officers of Taiwan in many occasions, but nobody gives a damn, okay, because they always like to brag that TSMC is blah, 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 blah. But the thing is, what if somebody else is coming up, okay, and you don't have, the second domain that you can rely on? That'll be a big tragedy of Taiwan. So anyway, this is a static dissipation. All right? So now this gives you the conclusion that I just said. So this is charging and discharging. So the square wave is on the top, is the input, and the ugly wave that generated, okay, from the V out, it looks like this way. So these are, if they are the equal size, see that? See that this way, okay? So the charging is slower, discharging is faster, something like that. Anyway, so check this out. The power, dynamic power, charging, discharging, blah, 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 equal to what? This one. This is I like you to remember. Remember what I said? Okay, for every cycle of the charge and discharge, when you charge, half of the energy you take from the power supply goes to the heat of a PMOS. When you discharge, the second half goes to the NMOS, it becomes heat. So this is a solution over here. For the dynamic power, it is equal to frequency times C times V squared. So this tells you the final answer, how to reduce the power. Okay, you reduce the frequency or the size or the voltage swing. Okay, you select one of the ways to reduce the energy. Any one will work. Okay, if you take 2 or 3 at the same time, that's even better. But in the meantime, you gotta be aware of one thing: you cannot lose the performance of the speed. Okay, the other term, okay, addressed in the dynamic power is called the short circuit dissipation. What is that? Okay, I use this figure to tell you what is that. Okay. Now this is an inverter, and we have a load over here. This is CL, okay, and we have an inverter over here. This is V in. So when this is low, we charge this one. When this is high, we discharge it. Okay, so the first term of dynamic power is about this part. Is that clear, right? That is the one I just showed you in the previous slide. That's the one over there. Okay, so the faster you do the charging and discharging, the more power it dissipates. That's why. But in every charging and discharging, okay, remember that our signal is not ideal. It takes time to travel. So this is V in. So there is a certain time during the transition. Over here, certain time. What is that? For example, when V in equal to half of the VDD, what's going to happen? This one will be turned on. This one will be turned on as well. Okay, so a small portion of the current, okay, will travel from the power supply to the ground directly. And this portion of a current does not go to the load. Is that clear? So when in the voltage is somewhere like this one, okay, because the V in here compared to the VDD here is low enough to turn on this one, it's high enough to turn on this one, so we are going to have a direct pass from the power supply to the ground. So that is what happened here. This part and this part. Okay, it's called a short circuit current. And this current has nothing to do with the logic operation. Okay, it is simple a waste of energy. All right, so you can do the mathematics here. You can consider this is a triangle wave. It's increase, decrease, increase, and decrease. It is a triangle wave. So if you look into the simulation of a waveform, you'll find out it has a small bump. Okay, I'll show you where that is. Here. A small bump over there. Okay? All right, and after some derivation, thank God, we have a very simple solution for that. Let's assume the rise time and the fall time is the same. So what's it going to have? We are going to have this final solution. Okay? Okay, it's relatively proportional to the VDD minus 2 VTH. This is 3 to the third order. But basically, you don't have any power to change this one. This is constant. This is constant as well. But pay attention to this one. It's a T rise. Okay, that is a rise time over the big T. Big T is a period. So how do we save the power? Pretty simple. Make these terms as small as possible. All right, because we don't have a power to change the other factors, right? So this is the only power we have. We reduce the T rise time. Okay, we can save a lot of the short circuits. Because when we reduce the T rise, that means we narrow down the gap, narrow down the window for the current that's going up and down. All right, that's how we do it. So that is why we always like to what? To have a square wave output. Because you make it as square as possible, that means the T rise become very small. Okay, that's how we reduce the short circuit power. Okay, and then you're going to ask me one thing, okay? What is the ratio, common ratio between the short circuit power compared to the charging discharging power? I will say the 10 to 1. That's according to my observation, okay? If you have not very sharp, but a gentle slopes of rising and falling, that about 10 to 1. That means dynamic power is still a larger one, 10 times of the of the short circuit power. All right, it's not too hard to remember these conclusions. Okay, So we have a very important observation about the low power design. Okay, basically right now we understand we want to save power, we save dynamic power. Okay, there are two terms in dynamic power. The first one is the charging and discharging, and the second one is the short circuit power. But there is an extra factor over here. It's called the alpha. Switching activities, which is not addressed up to now. Switching activities means that what is the probability that this gate is turned on? Okay, switching activity. Oops, sorry. No wonder the TA warned me. Oh, I have too many slides left. Okay. Now let me define what a switching activity is. Switching activity. Switching activity defines as, okay, when the output from 0 to 1. Okay, you might be wondering, how come we don't define the 1 to 0? It's the same. Okay, but we don't take both. If we divide it 0 to 1, of course, it will come back because it's always switching up and down. So that's why we only define it, okay, 0 to 1. That's why. All right? So let me check this way. Let's assume we have an AND gate. AND gate, right? AND gate. So we want to know the switching activity over here. What is that? When and how, what is the probability, okay, for this kind of phenomena happen 0 to 1? What is the probability? It's quite easy. So let's assume we have X or Y. Okay, no, A and B. I like to use A and B, and this is F. So we have A and B, and let's assume A and B are randomly given. So there are 4 possibilities. Is that right? 0, 0, 0, 1, 1, 0, 1, 1, right? Okay? Then, what is the outcome here? 0, 0, 0, 1. Is that clear? Everybody loved it? Okay? So according to this definition, okay, what is the probability the original state is 0? 3 out of 4, right? And what is the original stability? What is the probability for the next state to be 1? So the probability of 0 to 1, that is the switching factor, equal to and this is very simple. Even the kindergarten kids can calculate it. So as long as you understand the definition of switching activity this way. So the lower the switching activity, for example, it is hard for F to be switched because the probability is low. Now, if you check by the similar way to check exclusive OR, what's going to happen? Okay, the switching over here will become half times half, about a quarter. So technically speaking, if the probability for A and B inputs for both gates are the same, this one is less switched. This one will be more active, according to this table. And that's a fact. Is that understood? It's pretty easy. Okay? So right now I'll give you a bigger example. What happened if we have ABC, 3 inputs? So what you're going to get, ABC, you are going to have 7 zeros and a single 1, right? So the switching probability of this one will be that is smaller than that one. So basically what we can assume is that, okay, AND gate usually is used as a gatekeeper to quiet the circuits. It helps. Okay, but exclusive of gate, it does not. Because we have equal number of zeros and ones for the exclusive OR. All right? Is that okay? So this is a definition of switching activities. Don't panic. Okay? So we have add this switching activity. Basically, you can consider this is a probability to be activated. Okay, for the dynamic power. Damn, I wasted a lot of time. Okay, and I'm going to go over these pages quickly because it's about the leakage. And leakage is not that important in this course. I'm not saying it does not, I'm not saying it is not that important in real life, but in this course it's not. I'll tell you what. When we say the gate is cut off, that means the VG is equal to 0, right, for the AND gate. So that we assume there is no current. But if we go to the reality is, even though that we give a 0 voltage at the gate, we still see that we have narrow amps of current going under the water, under the surface. So it's not 0, but it's small. It's narrow amp. And most of the cases, when we do our circuit design, okay, it's about a microamp. So it's 1,000 times less. So most of the time, we just ignore it. But that does not mean it does not exist. It does exist, but we just ignore it, all right? So the current in cutoff does exist, but the thing is, it's small. It's small, okay? And remember the region that I mentioned is called the subthreshold region, is that when we accidentally increase the VG, the voltage at gate, okay, and then that means the gate is a bit open, then turn out that we have a small current going around here. It's about 100 times, 100 narrow amps, from time to times. But if you go over there, when it is fully open in the saturation region, it's over 1 million. It's a lot. So basically, that's what I say in this course. I always tell my students that this leakage could be ignored. Leakage source, subthreshold, and the gate leakage, that is what I already said. Too bad, I only have like 5 minutes left. Okay, junction leakage. Okay, and this is not important anymore. Okay, it's over here. Okay, diode leakage and tunneling. Okay. So leakage, basically, we don't have that kind of time, so we'll just ignore it. Okay, let me rephrase again. It does exist, but in your course, you don't have to care about it because most of the time your current is too large to overcome it. But besides the leakage and dynamic power, static power, the next thing we have to worry about is temperature. Temperature is a killer, okay? Every PC needs a fan. That's our TC. And maybe say, my phone does not need one. Okay, but the thing is, if you rip off your phone or your laptop, you're going to find out that on top of the CPU, there are some materials to dissipate the power, to spread the heat over the board to help you. So that means temperature is an important thing. So temperature, okay, when temperature is high, very high, so that reduces mobility. Okay, when temperature is high, you will feel very uncomfortable, the same as the device. Okay, you like to stay in the room with air conditioning, right? That will cool you down. Of course, you want to sitting in the freezer. Okay, it's too cold. But for those electronic devices, they like to sitting and working in a very cold environment. Okay, why? It's easy. When the temperature is low, it can help to dissipate the heat. It can remove the heat. The more heat is removed, the faster it can run. Okay, it has no problem. Besides, it helps that the device will not aging very fast. Number two is that V threshold is dropped. So when the temperature is high, because the VT goes down, some of the devices will be turned on automatically. So from time to time, you hear a lot of a car will get into busted or get into fire because under the sun. Because when the temperature is high, some of the electronic devices turn on automatically. And then when a sparkling appear in the gas tank, that will kill the car, okay? So basically temperature is the issue, and it's an important one. So the ion decreases with temperature. I-off increases with temperature. That is bad. That is really bad. We hate that. We hate that. Okay, it's about 5 minutes to 9. I'm going to give you the homework assignment because we have a long vacation coming up.